Number one, the drag force on large objects such as cars, planes, and skydivers moving through air at high speeds is given by d equals bv squared. Now, this force usually opposes motion, so sometimes you'll see a negative bv squared. Draw the free body diagram for an object of mass m that reaches terminal velocity. Too fast, I guess. Okay, so once it reaches terminal velocity, it's no longer accelerating, so it's in equilibrium. The downward force of weight is balanced by the upward force from the drag. Now, using that free body, we need to determine what the terminal velocity is in terms of the other variables. So I can set d drag force equal to weight. Plug in drag is bv squared. Plug in weight is mg. So I get the terminal velocity is equal to square root of mg over b. So we have the skydiver at 75 kilograms, and their terminal speed is 60 meters per second, and we're supposed to determine b. So b would be equal to mg over b squared. Plug in, and we get b is approximately 0.208 kilograms per meter. Number two, an 80 kilogram bicyclist and bike can coast down a 77-degree hill at a steady 2.64 meters per second. Ignoring rolling friction, the drag force is proportional to the square of the speed, so d equals cv squared. Draw the free body for the bike and the biker at terminal speed. Okay, so here's the biker on this 7-degree hill, and they're just kind of coasting at 2.64 meters per second. So the forces are balanced. And then write an equation to solve for c. I can say that the drag force has to be equal to the x component of the weight. The drag force is given by cv squared. X component of the weight is mg sine theta. Solve for c, I get mg sine theta over v squared. Plug in the numbers given, and I get c is equal to approximately 14 kilograms per meter. Draw the free body for the bike and biker if the average speed is faster than 2.64 meters per second. How can this happen? Write an equation based on your new free body and calculate the extra force needed. Okay, well in this case, if they're going faster than 2.64 meters per second, and the drag force would have to be more because it's related to the speed. So the only way that could happen would be if there was some forward force, and that forward force must be coming from the road. And how does that happen? Well, if the tires push back harder on the road because the person pedals, by Newton's third law, the road will push forward harder on the bike and the rider. It's still in equilibrium though, so I can set the drag force equal to x component of the weight plus the additional force from the road. And plug in cv squared equals mg sine theta plus the force from the road. Solve for the force from the road, and I get cv squared minus mg sine theta. And of course c we just found was 14 kilograms per meter, and the mg sine theta is 97.5 newtons. So you can see that the additional force is related to the square of the speed. Two drag forces act on a bicycle and rider. D1 due to rolling resistance, which is essentially velocity independent. That's kind of stuff that we've looked at already before this unit. And D2 due to air resistance, which is proportional to cv squared. For a specific bike plus rider of total mass 78 kilograms, the D1 is approximately 4 newtons, and that's not velocity dependent. It's constant. And for a speed of 2.2 meters per second, the second drag force is about 1 newton. Calculate C. Okay, so we know that D2, the second drag force, is equal to CV squared. And we know that at about 2.2 meters per second has a drag of 1 newton. Solve for C and you get approximately 0.207 kilograms per meter. Part B, what is the total drag in terms of V? Well, the total drag is going to be D1 plus D2. Plug in D1 is 4 newtons, and the CV squared, plug in as C is 0.207. get approximately the total drag to be 4 newtons plus 0.207 v squared. Determine at what slope angle, theta, the bike and rider can coast downhill at a constant speed of 8 meters per second. Well, d total has to be equal to the x component of the weight in that case. So mg sine theta is approximately equal to 4 newtons plus 0.207 kilograms per meter times v squared. And plug in all the stuff and solve for theta, and we get approximately 1.3 degrees. Number 4. A block of mass m with an initial speed of 5 meters per second slides along a horizontal surface lubricated with thick oil, which provides a drag force proportional to the square root of the velocity. So the drag force is negative bv to the 1/2. Draw the free body diagram for this situation. So here is the block sliding along this oil-covered horizontal surface. Here's the free body diagram with a normal force, a weight force, and a drag force. Notice this is slowing down. That's why we're having drag is equal to negative bv to the 1/2. Okay, so therefore net force must be equal to drag. Plug in that the net force is ma and the drag is negative bv to the 1/2 power. We can now plug in that a is really dv over dt. It's the time rate of change of the velocity. Divide both sides by m. Divide both sides by v to the 1/2. And we get dv over v to the 1/2 equals negative b over m times dt. Let's integrate both sides from 0 to, or excuse me, not from 0, from 5 to some v of t, and from 0 to t seconds. When I integrate, what happens is the power increases by 1, so it's going to be v to the 1/2 divided by the new power. So plugging in v of t and 5 meters per second, on the right hand side it's t to the 0 power, so it becomes t to the first power. And now we can move the minus 2 times 5 meters per second raised to the 1/2 to the other side and divide by 2. And then we can square both sides, have to do FOIL on the right. And finally we get an equation for the velocity. Now we want to take that velocity equation and we want to figure out an equation for position x. Well, remember that v of t is really the time rate of change of the position. So we can plug that in. I can multiply both sides by dt and then integrate from 0 to x and from 0 to t during that same time. And I get x of t is equal to b squared over 12m squared t cubed minus 5 or b radical 5 meters per second over 2m times t squared plus 5 meters per second times t. Okay, now we want to figure out the maximum distance the block slides. Well, when it reaches its maximum distance, the velocity will be 0. So therefore, let's use the velocity equation and plug in 0. Now let's solve for t when that velocity is 0. And when we do, we use the quadratic formula, and that simplifies to 2m times square root of 5 meters per second over b. Let's plug that into the position equation, and the last two terms will drop out, and so we get m times 5 meters per second times radical 5 meters per second over 3b. Number 5. A motorboat traveling at a speed of 2.4 meters per second shuts off its engines at t equals 0 seconds, and the drag force is proportional to bv. Draw a free body diagram. So here's the boat. Here's the free body diagram. Now complete the net force equation based upon the free body. Well, that would be the net force is equal to drag. Net force is ma, and the drag would be bv, and slowing down, so I'm going to put a negative there. Of course, a is really dv dt, time rate of change of velocity. I can divide both sides by m, and divide by both sides by v. Then integrate from 2.4 meters per second to some velocity via t in a time of 0 to t. And I get the natural log of v of t minus natural log of 2.4 meters per second equals negative b over m times t. Property of logs would be natural log of vt over 2.4 meters per second. I'm going to exponentiate both sides, and I get v of t over 2.4 meters per second equals e raised to the negative b over m times t. Then multiply both sides by 2.4 meters per second. So that's the velocity equation. It's an exponential. Okay, then of course velocity is really the time rate of change of position, so let's plug that in, and I get dx dt equals 2.4 meters per second e raised to the negative b over m times t. I can integrate from 0 to x dx, and of course I multiply the other side by dt, and I can integrate from 0 to t, and I get the position equation after integrating. We can now simplify, and finally we get the following. Okay, now let's figure out how far it travels before coming to rest. It's noted that after 3 seconds its speed has dropped to 1/2 its original value. Let's use the speed equation then. 1/2 its value would be 1.2 meters per second at 3 seconds. So we can use this then to solve for b over m or m over b. Natural log of 1/2 would be equal to natural log of e raised to the negative b over m times 3 seconds. And then we can solve this for m over b, negative 3 seconds over natural log of 1/2. We can then plug this back into the position equation, where m over b is given as negative 3 seconds over natural log of 1/2. We can evaluate this at infinity, so e raised to the negative b over m times infinity. Since that's negative b over m, that's the same thing as 1 over the quantity. So in other words, this is going to be a fraction, that second part. So 1 over e to the infinity. E to the infinity will be infinity. 1 over infinity is 0. Simplifying, we get 10.4 meters. So that's how far the boat's going to travel. Okay, number 6. The terminal velocity of a raindrop is about 9 meters per second, and the drag force is given by BV. Draw the two free bodies for the raindrop below. This is when it's less than the terminal speed and when it's equal to terminal speed. Which free body would you use to determine the value of the constant b? We'd use the one v equals v terminal velocity. So the drag force is equal to the weight force. B times 9 meters per second equals 0.003 newtons. So B would be equal to 3.3 times 10 to the negative fifth kilograms per second. Complete the net force equation for the free body. This would be F net equals weight minus the drag force. And of course plugging in MA for the net force and mg for the weight, and the drag is equal to BV. Divide both sides by m and do a little bit of algebra, and then of course acceleration is the time rate of change of velocity. I'm going to move the v minus mg over b over to the left hand side by dividing both sides by it and multiply both sides by dt. Then I'm going to integrate both sides from 0 to vt. That would be from 0 to t time. That'd be the natural log of vt minus mg over b minus the same natural log evaluated at 0. And of course on the right hand side is going to be negative b over m times t, because it was t to the 0th power. And then finally simplifying, rearranging, we get the following. Okay, now let's figure out how much time it takes for it to go from rest to 63% of its terminal speed. Using the equation we just had, 63% of that would be 0.63 times 9 meters per second. And we could divide both sides by 9 and then subtract the 1 minus 0.63, and that'll be equal to e to the negative 10 over 9s times t. And then we can take the natural log of both sides. And then finally we can multiply both sides by negative 0.09 seconds, or 0.9 seconds. And then finally solve for t, and we get approximately 0.89 seconds. Okay, the last one. You dive straight down into a pool of water. You hit the water with a speed of 5 meters per second, and your mass is 75 kilograms. Assuming a drag force of the form d equals 1 times 10 to the 4th kilograms per second times v, how long does it take you to reach 2% of your original speed? Ignore buoyancy. Okay, so you splash into the water, and you're going into the water, and you're slowing down. So there's going to be a drag force up and a weight force down. So the net force equation would be the weight force minus the drag. Of course, the net force is ma and weight is mg. Drag is given as 10,000 kilograms per second times v. A would be equal to g minus 10,000 kilograms per second over m times v. A is really the time rate of change of velocity, dv dt. And I can do a little bit of algebra on the right hand side. I'm going to multiply both sides by dt and divide both sides by v minus mg over 10,000 kilograms per second. I'm going to integrate both sides from 5 meters per second to some velocity, 2% of that velocity, which is 0.1 meters per second. And that's going to go from 0 to 2t seconds. Integrating both sides, on the left-hand side, I'm going to get a natural log. On the right-hand side, it's t to the 0 power, so it's going to become t to the first power. So it's going to be natural log of 0.1 meters per second minus 750 newtons over 10,000 kilograms per second. And then evaluate it at 5 meters per second on the left-hand side. On the right-hand side, we're evaluating between 0 and t, so the 0 part drops out. Just have the t left. Simplify the left-hand side using property of logs. And then multiply both sides by 75 kilograms over 10,000 kilograms per second. Negative 10,000 kilograms per second. And we get approximately 0.04 seconds.